calculate resistance? I haven't explained what is resistance, what is current, what is potential difference, how do we calculate resistance? Because it's possible that in a given circuit, you may have up to 3, 4, 5, 6, 10 resistors. If you open an electrical device like this one, definitely you see resistors scattered everywhere. So how do you calculate amount of resistance in accordance to the device that will be connected to those resistors? So let's start with this. Now, when resistors are connected in series, now let me quickly explain this. In an electric circuit, we have two ways that appliances can be connected. We have what is called a series connection, and then we have what is called the parallel connection, okay? When resistors are connected in series, the total resistance can be calculated using the formula below. What you have here is called series connection, where you have end-to-end connection, end-to-end. You can see 4 resistors connected to 3 ohms, connected to 2 ohms. This is the source. This represents the cell or battery. So when you have resistors connected this way, how do you calculate the total resistance? Very simple calculation, very simple. The formula you need for this is what I have here. So total resistance is simply the algebraic sum of all the resistors, in the circuit. So if it is a series circuit, provided it's a series circuit, just add everything together. And that is what we have there. So total resistance in this circuit, because it's a series circuit, is going to be R1 plus R2 plus R3. I want to believe that is simple enough, okay? That is simple enough. Let's move forward. Now, so total resistance, this is the calculation now, equals to R1 plus R2 plus R3. Then that will be equal to what? 4 plus 3 plus 2. And then you have 9 ohms. So the total resistance in this circuit is 9 ohms. I want to believe that was simple and that was straightforward enough. Now let's look at the second way that circuit can be connected, and that is the series connection. Look at this. It's different from the other one. Now in this one, what we have here is the resistors are arranged and each of their terminals are connected side by side. Can you see that now? Unlike in series, we have end-to-end connection. So this is parallel connection, where each of the resistors is actually connected to the same terminals. Now, when resistors are connected in parallel arrangement, the total resistance is what? Is the algebraic sum of the reciprocal of each of the resistor. Now, this is it. 1 over RT. RT signifies total resistance. Is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This dot signify if you have more than 3, just continue to add. Even if you have it up to 100, just continue to add. The formula is simple. 1 over R1 equals to all of this. But just ensure to bring this back to a normal, it's a reciprocal form. So when you do the addition, ensure to bring it back. Now this is what I mean. Total resistance is equal to, okay, this is actually a fractional addition of doing this, okay? Maybe I should still do this to show you what happened. Now we have 2 resistors here. So if I'm doing this in fraction based on this formula, that will be, 1 over RT equals to 1 over R1 plus 1 over R2. This is because I'm dealing with 2 resistors, okay? So this will be equal to 1 over 1 resistor is 4, and then plus 1 over 2, okay? So what do you do? This is purely mathematics now, addition of fraction, okay? So all I need to do is to find the LCM of 4 and 2, which is what? 4. Now 4 divided by 4 is 1. 1 times 1 is 1. Plus 4 divided by 2 is 2. 2 times 1 is 2. So this will give me what? 3 over 4. Remember, we have 1 over RT. So what I have here now is 1 over RT equals to 3 over 4. Remember, our target is RT, not 1 over RT. So what will you do? Flip. Whatever you do to the left, do it to the right. So if you flip, then this implies that R total will be equal to 4 over 3. And then 4 over 3 equals to what? That will be equals to 1.33333, as the case may be. So I just decided to do that to show you how that calculation was done. I want to believe that was clear enough. So let me continue with the slide. Okay. All right. So that is it. That is the calculation. And there you have 1.333 ohms. Okay. So we are still talking about how to calculate resistance in a circuit. The resistance of a conductor can be calculated using the formula derived from Ohm's law. Yeah. So what is Ohm's law? Yeah. Maybe I should just state it before I continue. Ohm's law simply states that the current flowing through a conductor is directly proportional to what? The potential difference across the conductor, provided temperature and every other physical constraint remains what? Constant. And don't forget, we have two types of conductor again, apart from the category I gave you. We have what is called the ohmic conductor, and then we have what is called a non-ohmic conductor. Ohmic conductor obeys Ohm's law. Non-ohmic conductor does not obey Ohm's law, and they fall into the category of semiconductor. So this is Ohm's law, which simply says V is equal to what? I. V proportional to what? I. Voltage is proportional to current, provided temperature and every other physical constraint remains constant. Okay? So if I remove the proportionality sign mathematically now, so we have V equals to what? KR. Now, what is constant? What is this K for? This K signifies R. So I can now replace this formula with V equals to IR. That is what you have here. So the voltage in a circuit is the product of current and resistance. I believe that is clear enough. So let's move forward. Okay. So in this formula, V represents potential difference, I represent current measured in ampere, and then R represents resistance measured in ohms. I believe that makes sense, okay? That makes sense. So let's move forward. Let's move forward. In cases where the internal resistance of a cell is involved, what will happen? Ohm's law will still apply, but then there will be a little modification on the formula to make room for what? Internal resistance. Okay? So this equation I'm about to show you now is an extension of Ohm's law. That is E equals to I into R plus R. Now, what's the difference? Remember the first formula was V equals to IR. So what did you see here? What happened is that V has changed to E, and then I still maintain its position, but then we have additional R coming into this. Okay? Now, whenever you have this, it means the potential difference here is actually referring to the total potential difference of the battery or the cell. So E here is called EMF, which means electromotive force, electron moving force, electromotive force. So whenever you have internal resistance of a circuit being involved in the calculation, you can no longer use V equals to IR. You simply use E equals to I bracket into R plus R. I believe that was clear enough. Don't worry, we are going to solve some questions using all of this formula for you to get it better. I've explained all of this. So V is EMF of the voltage, I is the current measured in amperes, R is the resistance measured in ohms, R is the internal resistance of the cell. Okay, so let's move forward from here. Let's look at an example, calculating resistance. A filament bulb, yes, we all have bulb at home. Yep, we do. Either a filament bulb or energy saving bulb or LED. But this one is actually referring to a filament bulb. Now, a filament bulb has a current of 20 ampere running through it with a potential difference of what? 100 volts across it. What is the resistance of the filament? Very simple question. All you need to do is to go through what I've just explained now. What do you have here? You have I. You have I, yeah? I equals to 20 ampere, okay? And then what next? You have the voltage, V is equal to 100 volts. What else? What is the resistance of the filament? We are looking for R, question mark. Now, which formula will handle this? Simple, Ohm's law. And what is that formula? V equals to IR. Since we are looking for R, what do? make R the subject of the formula. So R will be equals to what? V over I. Now substitute the values into what you have here. V is what? V is 100 volts over. What is I? I is 20 amperes. So 100 divided by 20, that means therefore the resistance we are looking for is 5 ohms. Very simple calculation using Ohm's law. All you need to do, outline all the parameters given in the question, use the formula, make the unknown the subject of the formula, substitute the values, and then play with the numbers to get your answer. I believe that was simple enough and very clear. So let's move forward. Let's move forward. Okay, I think I still did the calculation here. I just wanted to show you. All right, look at it. Look at it. V, I, R unknown. Recall V equals to I, R. So R, V over I. So when you play with the numbers, you get the answer. Was that simple enough? Yeah, of course. Let's move forward. Types of resistor. Very important. Types of resistor. Now, how many types of resistor do we have? Now, resistors are labeled based on the working principle. Remember, the primary function of a resistor is to do what? Oppose the flow of current in a circuit. But then we have different types of resistor. There are many. I'm going to mention two. And then, number one, we have what is called thermistor. A word comes from two words. The first part of it is therm, that is thermal. Thermal means heat. Then the last part is resistor. So if you combine thermal and resistor, you have what? Thermistor. Now, what does that mean? It means a thermistor is a component that has a high resistance when cold, but a low resistance when hot. In other words, we are saying that the resistance of this very material depends on what? Heat. Thermal means heat. So it changes its resistivity or its resistance value based on the amount of heat in contact with it. And then we have another one called the light-dependent resistor, LDR, light-dependent resistor. Now, a LDR has a high resistance in the dark, but a low resistance in the light. Now, this one is used mostly for automatic street light. Have you ever wondered how does the street light on the road work? Yeah, it's through the help of LDR. You don't need to switch it on at night or switch it off in the day. With the help of the LDR, you can possibly readjust the circuit and allow currents to flow when it is dark and then when it is day. These ones are also used in temperature or heat sensitive devices, fire alarm and all of that, because their resistivity or their resistance value changes with the amount of heat they are in contact with. Okay, let's move forward. Now, in a circuit, the following could be used to represent different types of resistor, which include. Now, what I'm about to show you is not a full circuit diagram, it's just for resistor, okay? Because I'm dealing specifically with resistance, potential difference, and current. So what I'm about to show you is just for resistor. So here we have resistor. Normally, the symbol for resistor, you can either use a sign, okay, a zigzag sign, or a rectangular box this way, okay? And then variable resistor. Variable resistor simply means you can vary the value, okay? We have those that are standard resistor. Standard resistor, you don't change the value. If it is labeled 2 ohms, that is what it will be. But variable resistor, you can always change the value to give you different values of resistor. So we have variable resistor. This is the symbol with a line, an arrow crossed on the resistor. So this means you can vary the value of the resistor. Then we have the thermistor. The thermistor, the heat-dependent resistor. This is the symbol. And then we have the light-dependent resistor, which is called the LDR. The arrow signifies light. So whenever you see this in a circuit, it means this resistor depends on light. Okay, let's move forward because we have a lot of things to do today. Electrical power. Electrical power. I've explained what is current. I've explained what is voltage, potential difference. I've also explained what is resistance. So what is electrical power? Yes, of course, we have electrical energy, so there must be electrical power. Electrical power is the rate at which an electrical appliance uses electrical energy. All appliances have electrical power rating. Yes, even this device I'm using right now, it has what is called electrical power rating. So how do we calculate electrical power? Power is measured in watts. Yes, even in mechanics, the unit of power is watts, okay? And 1,000 watt is equivalent to kilowatt. I want to believe we are familiar with this. When you are buying units for your prepaid meter, you always see something like this, 1 kilowatts, 2 kilowatts, and all of that. So 1 watt of power means that 1 joule of energy is used every second. 1 joule of energy. So 1 watt means you are using 1 joule of energy in every second. All right. Appliances that need to create heat, such as washing machine, cookers, hair dryers, kettle, usually use most power. So this device you are looking at, this device you are looking at consumes more energy. You'll be so shocked that this small electrical iron consumes more energy than the whole of this device that I'm using here because of the watt rating. In fact, some electric iron have up to 2,500 watts, while some television screen, I don't know how many watts this is, but some maybe 100, some 150. But anything heating elements, from electric heater, electric iron, they take a lot of energy because it's a heating element. And then TVs, radios, and computers usually use the least amount of power. So electrical power does not depend on the size of the appliances, okay? The appliance might be very huge and large like this, but the power rating may be small, all right? So let's move forward. Electrical power. Now, in electrical devices, power can be defined as the product of current through the device and voltage across it. Now, let me quickly differentiate this. Normally, the definition for power in mechanics is simply energy over time. Energy over time. That is in mechanical power. But in electrical power, the definition is different. The definition is simply current. Current times voltage. So take note of that. Power in mechanics is energy over time, but power in electricity is current times voltage. So that is to say electrical power P will be equal to what? IV is the product of current and voltage. The product of current and voltage. All right? So the relationship between power, current, and voltage is shown below in the equation. And that was the equation I just gave you now. P equals to what? IV. P stands for power measured in watt. I stands for current measured in ampere. V stands for voltage measured in volts. All right? I've explained all of that. Let's move forward. Let's treat one question before we go further. A filament bulb has a potential difference of 200 volts across it and a current of 0.2 ampere running through it. What power is the filament bulb operating? I like using common examples around so that we can relate with it, okay? So how do you calculate the power of a simple filament bulb in your house? This is how you do it, by simply using the formula I gave you here. So how do we go? Let's see how to go. So list out all the parameters. You have V. V was given as 200 volts. That is it. I was given as 0.2 ampere. So we are looking for power. Then ask yourself, which formula relates power, current, and voltage? So bring up that formula that I gave you before now. Recall, P equals to IV, right? So what do? Substitute this value into the formula to calculate the power. So that is how to solve it. So a simple filament bulb at home that consumes 200 volts at 0.2 hour will be rated 40 watts. I want to believe you must have been seeing this rating on electrical bulb. Energy saving bulb, they are not as high as this. In fact, some energy saving bulb are as low as 10 watts. That is why they are called energy saving bulb. Meanwhile, the filament bulb, one filament bulb, like in those days, in the 80s when we were using the filament bulb and all of that, one filament bulb can be as high as 100 watts. But today, with advancement in technology, one filament bulb can be split into by like about how many now? If you are using energy saving bulb of 10 watts, that should be 10 bulb. which of course can go around the whole building, compared to one filament bulb in those days consuming 100 watts. Okay, let's move forward. Let's move forward. Okay, I think this should be the last thing for this before we move into solving question. Ammeter. Yes, in electric circuit, we have instruments, we have devices for measuring different parameters. Remember, I mentioned those parameters. Current is one of it, voltage is one of it, okay? Resistance is one of it. So how do we measure the current in electric circuit? This is the device. It comes in different pattern, okay? Different pattern. You may see other ones that are different from this. But why I bring this one up, this is the one we use in the laboratory, okay? Now, an ammeter is an electrical measuring device that measures electric current in ampere. That is the work of an ammeter, okay? And that is the simple structure of how an ammeter looks like. If you go to your physics lab, check any device you see with the symbol A. A stands for ammeter. Now, an ammeter is connected in series. Take note of that. In case you want to do your physics practical, don't connect the ammeter in parallel with the components. Connect it in series with the components. That is how to connect ammeter. Ammeter actually measures the total current flowing in the circuit, or if it's a parallel circuit, the current flowing in a particular section of the circuit. Now, for this circuit, this is a one-loop circuit. Of course, it's a series circuit. So don't connect the ammeter across the resistor. Don't. Ammeter should be connected in series because it measures the amount of charge flowing through the circuit. So an ammeter is connected in series. This is the connection, how ammeter should be connected. Okay, let's look at another one. Voltmeter. A voltmeter is an electrical measuring device that measures what? Voltage. So if you go to your physics lab again, check to see a device with the label V. If the label is V, it means it's a voltmeter. If the label is A, it means it's an ammeter. If the label is G, it means it's a galvanometer. But notwithstanding, we have one device that can do the work of all these ones I've mentioned here. And they are simply called multimeter. Multimeter. So if you have one meter that can measure all of this, we call it multimeter. But for now, because of physics practical, I have to differentiate each and every one of them. So this is what a voltmeter do. And how do you connect it? You connect it parallel to the components you want to measure. Unlike the ammeter, it was connected in series, okay? But voltmeter is always connected across the components to be measured. That is how you connect a voltmeter. But my emphasis in this very slide or in this very lesson is not really about the ammeter and the voltmeter. My emphasis is on this, galvanometer conversion. Because over the years, I've seen past questions from WAEC, that has to do with this, how to convert ammeter to galvanometer, how to convert ammeter to voltmeter. So I decided to go through this just to show you how we do that. So let's move forward. Now, this is a galvanometer, okay? Galvanometer is a very sensitive material. Sometimes they don't measure, sometimes they are using detecting. But this one has been, modified to detect flow of current and also measure. Galvanometer is a device that is used to detect, that's the primary purpose, a small electric current or measure its magnitude. Yeah, galvanometer can detect a very small amount of current, okay? But then, if you don't have a galvanometer in your laboratory, but you have ammeter and voltmeter, what will you do to use the ammeter and voltmeter as a galvanometer? That is what I want to show you now. How to convert galvanometer to ammeter, how to convert ammeter and voltmeter to a galvanometer. Now, a galvanometer is converted into an ammeter by connecting it in parallel with a low resistance called shunt resistance. Now, what is the idea behind this? Let me show you the circuit quickly. Now, remember, according to Kirchhoff's law of current and Kirchhoff's law of voltage, this is the current flowing through the circuit, okay? Now, if you have current flowing through the circuit, just like this now, this is the incoming current. At this point, this current will split into two to give you I1 and then I2. Now, I1 is the one going to the galvanometer, and then I2 is the one going to the resistor. So the resistor used in converting an ammeter to galvanometer is called shunt. Take note of that. The resistor used in converting ammeter to galvanometer is called shunt. What is the physics principle behind this connection? Galvanometer can only measure small current. So in a situation where I want to use it to measure large current, to avoid the galvanometer being damaged, what will I do? All I need to do is to divert greater amount of the current by connecting a resistor in parallel. So the function of this resistor is to do what? Divert greater amounts of the current. You can see the line looks bigger than this. So greater amount of current has been diverted to this resistor called shunt, thereby allowing just small currents to go into the galvanometer. So in other words, what I'm trying to say is to convert ammeter to galvanometer, connect a resistor in parallel to the galvanometer. With that, you have successfully converted a galvanometer, an ammeter, to galvanometer. But then, the problem is not the connection. The problem is calculation. Sometimes WAEC will ask you some funny question about this. So I'm going to show you what to do quickly. Now, RG represents the resistance of the galvanometer. You can see that here. And then G represents the galvanometer coil, right? And then I represent the total current passing through the circuit. We know that already. IG, I sub G, represent parts of the current that has been splitted from this junction to the galvanometer. Then IRS represents the resistor that is used in converting ammeter to galvanometer. I keep emphasizing on that because I've seen questions about this very resistor. You see, you see questions like the resistor used in converting ammeter to galvanometer is called what? So take it from me, it's called shunt. Don't forget. Now let's move forward. Yes, there are formulas to do this. The PD across the galvanometer and the shunt is the same. According to Ohm's law, when circuits are in series, the same current flows through them with different potential difference. But when circuits are in parallel, different current will flow through them with the same potential difference. So what we have here simply says the total voltage is the voltage passing through the galvanometer. VG means voltage through galvanometer, and then VS means voltage through the shunt. So why this is happening is because the circuit is a parallel circuit. In parallel circuit, the currents, they are not the same, but voltage is the same. So this is where you start with. If you can get this idea, then you'll be able to get other formula. All right. So the total current in the circuit is the sum of the currents. Why are we adding? Remember, there was a branch, there was a junction. Let me show you that again. There was a junction. Remember, the total current was coming this way. One went to the galvanometer, and then the other one went to the shunt. Here we have IG, here we have IS. So that is what is happening. So the total current in the circuit is the algebraic sum of IG plus IS. With this, you can form an equation for calculating how to convert ammeter to galvanometer. Let's move forward. Now, combine equation 1 and 2. Combine equation 1 and 2. If you combine equation 1 and 2, then you have RG times IG will be equals to I minus IG times RS. I don't want to scare you with this. Let me quickly explain how we arrive at this formula. Now, what this simply means is this. Let me quickly explain. Remember, here we have VG equals to VS. So the whole of this is VG. And then the whole of this is VS. How? Please pay attention. Now, VG, remember from Ohm's law, V is equal to IR. So if I'm looking for voltage through galvanometer, all I need to do is to multiply the resistance of the galvanometer by the current in the galvanometer. Okay? Now, coming to the shunt, if I'm looking for the voltage across the shunt, all I need to do is to multiply the current by the resistance of the shunt. But it's not going to be I, because part of I has been given to IG. So what is left for the shunt is I minus IG. Does that make sense now? So this is the formula used in doing any calculation that relates to conversion of ammeter to galvanometer. All right. Now, a suitable resistor called multiplier. Which one is this? So this one is the second way of converting voltmeter to galvanometer. The first one I just explained is ammeter. So how do you convert voltmeter? Now, I know in physics practical, sometimes you may not have galvanometer to do what you want to do, but if you know how to do this conversion, you don't need to worry. Pick up any ammeter in your laboratory, pick up any ammeter in your voltmeter, and then use this simple logic to convert them to a galvanometer. So, what is the physics principle behind this? To convert a voltmeter to galvanometer, connect both components in series. Connect both components in series. Now, what is the idea behind this compared to the first one? It's very simple. Now, according to Ohm's law, in series circuits, the same current flows, but different potential difference. So if I wish to use this galvanometer to measure a larger voltage, all I need to do is to bring up a resistor that will take greater chunk of that potential difference or that voltage, thereby saving the galvanometer. Okay? So that is what is happening here. Now, just like what I said before about shunt, the resistor used in converting a voltmeter to galvanometer is called multiplier. I'll say that again. The resistor used in converting a voltmeter to galvanometer is called multiplier, while the resistor used in converting ammeter to galvanometer is called shunt. Does that make sense? Okay. Now, let's move forward. Okay, I've explained all of this. And then let's quickly see the formula. Now, the PD across the circuit is the sum of the PD across the galvanometer and the multiplier. Okay, how did we arrive at this formula? Let me explain again. In series circuits, the same current flows. In the same series circuit, the potential difference is the algebraic sum of the potential difference on each of the circuit. So what we have here is as a result of, this is VG, voltage in the galvanometer, plus voltage in the multiplier. And according to Ohm's law, V is equal to IR. So if I'm looking for VG, all I need to do is to multiply IG by RG. If I'm looking for VM, all I need is to multiply IG by RM. Yeah, I thought somebody would ask, why do we have IG and not RM? The reason is because this is a series circuit, and in series circuit, the same current that flows through the galvanometer is the same current that flows through the multiplier. So IG and IM is the same thing. Does that make sense? Okay, let's move forward. All right, so the total current in the circuit, IG equals to IM, and then we can end it there. Now it's time to attend to some questions.